Okay, this next problem is also a topic 5, paper 2 question from 2019. An electron is placed at a distance of zero point 0.4 meters from a fixed point charge of negative 6 millicoulombs. Show that the electric field strength due to the point charge at the position of the electron is 3.4 times 10 to the 8th newtons per coulomb. Okay, well here we're looking for the electric field strength, not the force, but the electric field strength. And in case you've forgotten what that is, well, this is one of those problems that asks you to show. So that means that the answer is given here, and you can see the units of the electric field are newtons per coulomb. So I hope everyone can remember that the force, the Coulomb's force, is your sort of classical fundamental force um, equation. It's in the form of the two properties times each other divided by the distance squared and some constant. So either with gravity or with the electrostatic force, it's going to be, for example, mass times mass over r squared. In this case, it's charge times charge over r squared. That would be the force, and you'd have a constant in front of that. So if it's going to be newtons per coulomb, then what I'm going to have is I'm going to have that equation, which is Fk Q1 Q2 over r squared. And if that is the force, then the electric field is going to be equal to a force per unit charge. This is an equal sign. So what gets divided out here is the test charge, if you will. So remember we talked about a small positive test charge is what we use around any given charge to help construct the electric field around that charge. So this is so the electric field strength then is going to be equal to K Q over R squared. And that gives me the proper units as well. Plus, of course, I mean, this formula is in the book. It's in the formula booklet. Here it is. It's K times Q over R squared right here. But in case you forget, I hope that what I've said here makes sense. So K here is given. This constant is in the formula booklet. We have a charge of 6 millicoulombs. That's a huge charge. It's right there. And then over the distance squared, 0.4 squared. And that is all right here. Let's go ahead and just, let's do that though. So that's 8.99. 8.99 times 10, and that's to the ninth power, about 9 to the ninth. Okay, times 6 times 10 to the negative third over 0.4 squared. So times 6 times 10 to the negative third, and then that is this whole thing divided by divided by 0.4, and that's squared. Okay. And that gives us 3.37. So we're looking for, it's going to be a large field strength. That's a very large charge. Remember, a coulomb is a huge amount of charge. And even 6/1000ths of a coulomb is a large amount of charge. That represents a lot of electrons. 3.37, how did we do here? 3.37, 12500, and this is 337 million. Okay, so all right, good. I got that. We're not worried about the sign right now. Not sure why, but it would be pointing, since this is a negative charge, these are going to be repellent forces. They're going to point away from each other. We've got a negative charge, and then we place this electron over here in the field at 40 centimeters away. Next question says, calculate the magnitude of the initial acceleration. Well, since I have the force per unit charge, that's what I've calculated here, right? This is the force per unit charge. I just have to multiply it by the charge to get the force. But that's the same thing as going up here and using this equation, right? I divided by the the charge here. I'm going to multiply by that charge again, and now I'm going to get the force. I didn't use it this time because I was looking for the strength of the field. And so we know the charge on an electron. It's 1.6 times 10 to the negative 19th. So I take my answer and I multiply it. So I take the answer that I got here and I multiply it by the charge on an electron, and I get this number here, 5.4 times 10 to the negative 11th. Let's just confirm. It's always good to actually calculate yourself. Don't just look at it and say, yeah, sure. Punch the buttons. So let's take our answer from before, multiply this. Let's take our answer times 1.6 times 10 to the negative 19th. Oops. I have to raise it times 10 to the negative 19th. And I get about 5.4 times 10 to the negative 11th. 5.4 times 10 to the negative 11th. Looks good. Checks out. Okay. And so this would be the force, though. We're not done. This is the force. We don't want the force. We want the acceleration. So, of course, F is equal to ma. So A is going to be equal to the force divided by the mass. And the mass of an electron, of an electron in this case, is something we can look up in our formula booklet, and it's 9.1 times 10 to the negative 31st. So we take that and 9.1, we take our answer and divide it by 9.1 times 10 to the negative 31st. And what we get here is 5.9 times 10 to the 19th. And what do we have here? 5.9 times 10 to the 19th. Looks good. That's an enormous amount of acceleration. Again, it's a very large, it's a very strong field. That's a lot of charge. So this is a lot of acceleration, a huge acceleration. Describe the subsequent motion of the electron. So let's see what's happening here. We know that we have, at a certain distance, there's a certain force, and that certain force we calculated. We calculated it up here. This is the force when the electron is 0.4 meters away from the charge of 6 millicoulombs. It's going to move away, and as it moves away, of course, that force is going to get less. So if the force gets less, then the acceleration will be less. So the electron will be repelled by this this negative 6 millicoulomb charge. It'll be repelled at an initial force given here and an initial acceleration given here. But as it moves further away, the force decreases, so the acceleration decreases. Now, the acceleration means that the velocity increases. So the velocity will continue to increase while the acceleration decreases. So that's what we're looking for in the answer here. The electron moves away from the point charge to the right along the line, away from it. We have a decreasing acceleration, but an increasing speed. We have an acceleration, so that means our speed is increasing, a change in velocity. But the acceleration itself is a function of the distance, and so that will decrease. So you need to say both of these things, okay? You have to make sure that you got three things here, really. The direction, away, the fact that the acceleration is decreasing because the force is decreasing, because the distance is increasing, and the fact that the speed is increasing. Even though we have a decreasing acceleration, we still have an acceleration, and that means an increase in speed.